Hey listeners, welcome to the final episode of 2021 of the ALD Stories podcast. This month, we find ourselves back in the Netherlands, about 130 kilometers northwest from Eindhoven in Delft. You might know Delft from the blue-painted porcelain Delftware, or maybe the Baroque painter Johannes Vermeer, but those of you paying close attention to our previous episode may already know why we are coming to Delft. That's right, our guest this episode is Ruud van Ommen, professor of chemical engineering at Delft University of Technology. Ruud is known for his work on particles, understanding their surface chemistry, how they interact, and most importantly, coating them with ALD. Atomic layer deposition on particles has found quite a large number of uses, particularly for pharmaceutical, catalysis, and battery applications. So much so that a plethora of companies focused solely on coating particles with ALD have been spun out, including one of Ruud's own, Delft IMP. In this episode, Ruud and I chat about the challenges that come with coating powders compared to flat substrates, the process of industry scale-up, Ruud's work on coating pharmaceutical powders, and a small chat on atomic layer etching of particles. A big thanks goes to Ruud for all of his time and his insights in producing this episode. If you're enjoying this content, please subscribe to the Bennick YouTube channel so you never miss an episode, and please leave your thoughts down in the comments. So without further ado, grab your tea or your coffee, and please enjoy episode 9 of the ALD Stories podcast.
Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Bennick, the home of ALD.
Well, thank you again for joining me today, Ruud.
Yeah, thanks for having me on this podcast. It's a pleasure to be here and tell a little bit more about the work we're doing in my group, especially on particle ALD or powder ALD. You can use both names.
Maybe to start, you can just chat about what powder ALD really is and why it's kind of a more difficult thing to do, a departure from our typical ALD. If you can talk about maybe what the fluidation of powder is and why, what that means for ALD and what approaches for powder ALD exist in that context.
Well, first to explain perhaps to our listeners a little bit of the basics of that. Powder or a bunch of particles, I often use it kind of interchangeably. That's an amount of grains of solid material. Those elements, those particles, they can widely vary. You can think of grains of sand. You could even think larger, like coffee beans, and even we do even coat nanoparticles in nanopowders. Over the years, I've been discovering more and more applications why you would like to coat particles in general and why you would like to use ALD for that. Perhaps good to realize that coating of particles is already done for decades in industry, and then mostly on the larger particles to protect them or to give them some additional functionality. And then often they do that with liquid phase coating. So they spray a liquid on a powder, and then you get a film, typically in the order of micrometers. And one way to do that was already in a fluidized bed. And a fluidized bed is basically a vessel that you fill with this powder, and you blow gas from the bottom through your bunch of powder, your bed of powder. And if you do that at a gas velocity that's high enough, then your particles will start moving around. They get what it's called fluidized, and it behaves a little bit like a quicksand type of stuff, but then not with water and sand, but with air and sand, or with another gas and another bunch of solid particles. So the trick is that you blow hard enough that your particles start moving, but not too hard that you blow them out. But there is normally quite a range of gas velocities that will work to this extent. And of course, it depends on how large your particles are, how hard you will have to blow. And once these particles are lifted and they're moving around, they're also mixing quite well. So that's good, for example, what they did in the past and still are doing, but already did do for quite a while, spraying liquid on it to form this liquid film and coat particles in that way. Then you leave it dry, and then you have a core shell type of particles in the end. But actually, it was realized that I can go a bit into the origin of that later on. But actually, with ALD, this would also be quite nice, especially when you look at small particles. Yeah, then liquid films become way too thick with micrometers, and that for a number of applications, it would be nice actually to have a very tiny film of only nanometers on particles. And that's of course something like, the listeners to this podcast, most of them will be themselves experts on ALD, will appreciate that ALD is a great technique to achieve that. Since the surface area is so huge of those particles, you need to feed in much more precursor, and that typically means much longer pulse times. So instead of being sub-second pulses, you typically have pulses of tens seconds, a couple of minutes, often depending on the size of your bed. And with fluidized beds in our lab, when we have a couple of grams of nanopowder, we easily have 100 square meter. And then you can imagine that that's taking quite a bit of precursor. So that means a long pulse time for the reactants.
And then what is the purpose of fluidization? This is because of the high surface area of the particles. You need to be able to expose all of the surfaces and to the precursors that are being introduced.
You could also just have the particles in rest, lying on top of each other, and that's what they did do in Finland in catalyst preparation. But even already before, in the 60s, in the really early days of ALD in the USSR, they often used silica gel. In most cases, also that was stagnant, and that has two disadvantages. First, you can have touching points between the particles that are not coated, but I would say that that's not the biggest problem, because if you think of spherical particles, then the touching points are only very minor, and most of the area is still being exposed, and it depends on the application if you can live with those pinholes or not. More problematic thing is with particles being in rest, the mixing between your gas and your particles is more cumbersome. They also showed in some papers that you will have a reaction from through it. So the first surface that's hit by the gas, let's say if it comes from the bottom, there first the ALD will take place, and then the front will move up. Of course, ALD is self-limiting, but you have to be very careful with where the front is. That's one thing. And also in the actual direction, whether it's more to the one side or the other side wall, you have to be very careful that this gas flows very evenly through your substrate, to your powder substrate. And if you might not waste ALD by having shortcuts in your system. And then the advantage of this fluidized system, the powder moving around, is that you have a much better mixing and more intimate contact between the gas and the particles.
And this fluidized bed, would you say that this is the most common way that particles are fluidized, that particles for ALD have been moved around?
There are a couple of ways. I guess if you look to the past, Russia, early Finnish work, that was mostly on packed beds. These days, the past almost 20 years, most emphasis has been on fluidized beds. Al Weimer in Boulder and my group have been doing that a lot, and then also some other groups around the world have been picking that up and really be using it as tool, but the majority. And the group of Steve George, but also Christophe de Tavernier in Ghent in Belgium, they use rotary reactors where you rotate a drum. So the particles are not moved by the gas flow, but by the rotation of the drum that they are in, rotating cylinder, which keep the particles into movement. Of course, 4 groups is very little statistics, but I think there is some correlation that both Al Weimer and I, chemical engineers, use a fluidized bed, and the other 2 groups are respectively chemists and physicists and use the rotating drum, because I think that's a great lab scale equipment. Of course, you could also do it at a larger scale, but if you really think about industrial application, you will see that there are many processes using fluidized beds in industry. I'm not talking ALD, but just in general, in the process industry, fluidized beds are being used all over the place. And rotating cylinders you will encounter once in a while, but that's not that common. And for good reason, to have rotating elements and particles in there and so on, that is a bit cumbersome, I would say. So for the lab, both approaches are great, but I think and that's one of the things we like to think about as chemical engineers. If you think about scale up, then probably the fluidized bed is the better way to go. With one pointer there still, it depends on the fluidized bed which product you are making, and many of the fluidized beds out there in industry, when you process particles, they feed in some particles, and at the bottom you get out some particles. Now that's something that's not very compatible with the ALD cycles, because in our case it's really a very peculiar process with transient dynamics, whereas many other processes, for example, if you continuously spray liquid on your particles, it's a completely continuous steady state process. So you can add particles and maybe get out some heavy particles from the bottom, and that's an ALD not very well doable. So that's why we also started to think, can we move from the batch operation in a fluidized bed to continuous operation? We started to think about pneumatic transport of particles. So blowing particles through a long tube with a higher gas velocity, the higher than the fluidized bed, and injecting your precursor along the way. Mm-hmm. While they are being blown through the tube, you inject the reactants, you carry out ALD, and you get your coated material out at the end.
This is kind of a spatial approach to doing.
Yeah, exactly. That's what in ALD terms we typically call a spatial reactor, and in the chemical process industry, well, they typically talk about continuous processes, like most things, like oil refineries and many other things. Are you put something continuously in at the end, you get a product continuously out, and that's typically more liked than making a batch, putting it out, and making the next batch. You see even in other sectors, like in pharma, with completely other processes also there, they want to go from batch processing to continuous processing.
Yeah, I don't talk, or I haven't at least talked about the work that I've done in the past so much on this platform so far, but this is an area where I know a little bit about. When I was working in Steve George's lab, I did some particle MLD, and yeah, you're exactly right. We used rotary reactors in Steve's lab, and even going from, or at least we were attempting to go from to a very tiny scale up. So just from doing a couple milligrams of powder up to maybe a gram or two, and even scaling that up on a pretty tiny lab scale was really difficult to do in the rotary reactor. Ran into immense problems, a lot of agglomeration issues, a lot of kind of mechanical add-ons that we ended up integrating into the system to try and combat some things. But that brings up a good segue into talking about the scale up of particle ALDs. There are an enormous number of industries that are interested in having surface functionalized particles, whether it's the pharmaceuticals like you mentioned, or the battery world, or people for catalysts, and you have a little bit of experience in scaling up this process. Maybe you could speak into how that scale up process works, and what the differences between the scaled up PALD looks like compared to the lab.
Yeah. No, that's really a good point, and something that's really close to my heart. You already mentioned in the rotary reactor, you might suffer from the cohesive nature of powders, and I would lie if I would say that in fluidized beds you don't have these problems, because also there you might run into sticking of powders and things like that. So one first thing is that you get control over the fluidization or the movement of your powder, and if you have difficult powders, cohesive powders, that especially happens when you have pretty small particles, you need often, in addition to the fluidization in our case, some assistance method. And there are a number of those, but one that we use often in my lab is having the fluidized bed on a vibration table. So the vibration action loosens up the bed, simply said, and also prevents that you get preferential pathways of the gas bypassing the rest, and makes for a nicer homogeneous fluidization. People that are transporting biomass pellets and so on, often the vibrated type of systems are used there as well. And that's of course important, because when you talk about scale up, it's going to larger length scales, but typically also going to longer operation times. In the lab, you might be using the reactor for an hour or a few hours, where out there in industry, typically they want maybe maintenance should have maintenance shutdown for once a year, but for the rest it should just operate. So then it is very crucial to have something like vibration, and you can also think of high velocity jets or something like that, to loosen up the material and to keep things going. And the other thing to think of when scaling up, especially for fluidized beds, is precursor dosing and how to size your equipment. You are blowing the gas through the bottom of your bed, and basically the wider I make the beds, that doesn't do much difference to how the particles behave. They still need roughly the same gas velocity. So if I make the cross-sectional area 2 times as large, I need 2 times more gas, volumetrically speaking, but I still have the same local gas velocity. So I can make it very large, and that doesn't matter. Meaning that if I would keep the same height of powder, I can also feed the same amount of ALD reactant in that time. So the one thing you could do is try to increase your concentration of your reactant, but that might be tricky, maybe because the vapor pressure is not that high, or maybe you might run into amounts or concentrations that you don't want, like with trimethyl aluminium. And the other way to do it would be just to increase the pulse time in order to have a long enough time so that you feed enough reactant ALD reactants to cover all your particle surface.
What is a typical batch size that you can use, or maybe a throughput in weight that an industry could get per day for powder now that it's been optimized a little bit more?
So in our lab, typically, often we make a couple of grams in fluidized bed when we do some test sometimes on a catalyst, other times on a pharmaceutical. And we can also in our columns make 100 grams or something like that. But when you go out to industry, then you earlier talking about tons you want to make. But like I said, we've been also looking at the continuous system, and that's what at the moment we're mostly looking at. And for that reason, also there's a spin-off company from my group called Delft IMP, which stands for Delft Intensified Materials Production. And they are going further in scaling up this kinetic transport of the particles and the reactor that belongs to it. And they now have a system that can produce 10 kilogram per hour. And they just have been raising an investment of 10 million euro in order to make a system, an installation of a factor 10 larger, so that they can produce 100 kilogram per hour. And if you are at 100 kilogram per hour, then you are in the range that certain companies with specialties get interested in. Could be like specialty pharmaceuticals. The outlook of Delft IMP is after that to go even a step larger, so that you make a system of a ton per hour, and then you're more entering into markets like catalysts, batteries, and so on, that really require larger volumes.
Those are enormous amounts of powders for those that are that maybe haven't worked on powder ALD before. Typical experiments are on like milligrams. I feel like, particularly at least what the ones I worked on. So fill a room with these powders, and that's what's going through every day. You bring up a couple of things that I like to touch on.
Okay, yeah,
One,
great.
definitely a congratulations is in order to Delft IMP for their Series A funding. That's really fantastic, and I'm really happy to hear about that. Pulling that thread a little bit more, I know that you were a visiting scientist at my former university, my alma mater, University of Colorado. And I'm sure you're familiar with the particle ALD companies there, the ALD Solutions that was started by Al Weimer and my former PI, Steve George, and Forge Nano as well. When you were in Colorado, did you work on powders with any of these folks when you were visiting?
Yeah, I've been working at that time in the lab of Al Weimer, visiting there during summertime, and we've been working with people there on particle ALD, and especially also on this microjet to enhance fluidization. Yeah. And I've been visiting at that time also ALD nano solutions and so on. So sure, now that's yeah.
Yeah, it's great to see Delft IMP joining the rush for particle ALD.
Yeah, no, and I think that there are so many opportunities out there, and companies, the bigger companies, they really start to get interest right now. That it's also making sense that there are more parties on the market, also with some different technologies. I would say that from the point of view from the big chemical companies and so on that might be interested in particle ALD, it might be also more worthy to them that there are multiple providers out there. I mean, if there's one single company just pushing this technology and no one else, you might also wonder how large the risk, of course, for a big company is just to so I think if you look globally at it, it's great that there are now multiple players in the market.
I'll probably say it many times during this that particle ALD is so near and dear to me, and some of the applications for it are, I think, some of my favorite that ALD goes into out of these industries that are kind of outside the normal semiconductor manufacturing, and maybe that's a good way for us to get into some of the work you've done in these particular applications. And one of them I think is great is it feels a little bit like a departure from normal material science and normal kind of physical chemistry and these types of things is the work of coating pharmaceutical powders. And I know you can do both ALD, you can do MLD on these powders. I've done a bit of both. And maybe you can talk a little bit about what the challenges are with pharmaceutical powders versus our typical inorganic oxides that we might be coating.
Yeah, so first perhaps what we wanted to achieve over there. I was several years ago in a big EU project, which was on particle technology in general, and we were bringing in particle ALD over there, and there was a researcher and senior scientist from AstraZeneca based in Gothenburg, Sweden, Staffan Forderstad. He was also involved, and he was really interested in what we were doing. So we started talking. I came over and presented our work and so on, and that developed then in a much larger collaboration. Where first the primary target was to controlled release, and not so much for very specific application, but more to have ALD in their portfolio as a platform technology. And I also learned a lot of things along the way about pharmaceuticals myself. First of all, I thought in controlled release, well, that's instead of a patient taking a pill 3 times a day, you only need to take it 1 time a week. So when our first result with very thin films only indicated that we slowed down the dissolution by half an hour or full hour, I was very disappointed because I thought, well, we are very far away from this full week. But actually, the folks at AstraZeneca were very enthusiastic because they said, no, this is also very good controlled release. Because when a patient, and we were having as a model system inhalation medicine, so where you have these dry powder inhalers that treat asthma or so, when people get it in and it dissolves right away, they get like a peak concentration in their blood, which is very unhealthy. And if you slow that down and spread it more over an hour or so, this dissolution process, then it's much better for the patient. So in that way, controlled release is not decreasing the number of times you have to take it, but just making the single dose much more healthy to the body. Another thing, and that was especially because we used dry powder inhalation as a model system, is that the coating improved the flow behavior of the powder. Because in the fluidized beta particles should nicely move, but also in such a dry powder inhaler, they should flow out and follow the gas flow through your mouth into your lungs. Also there, it's important that they are not sticking too much and so on. And the surface treatment with ALD, and I'll come to the materials in a moment, can help in making this flow behavior much better. And the third one that we only explored very superficially so far in the project, just also because of lack of time of the PhD student who worked on it, Damiano Lazara, who did really great work and a number of nice papers out there, especially on the controlled release and on the flowability. And the third point only we touched very little, but which could also be important, is the shelf life of pharmaceuticals. And if you give them a coating, that they are much less sensitive to humidity, and especially in higher temperatures. And you might think perhaps of developing countries where also storage facilities are maybe not that good. You can, with this coating, give a larger lifetime to your medicines.
It's interesting that you note that you can increase the flowability of these particles by using ALD. So that must mean that pharmaceutical powders don't flow super well to begin with. In which case, then was it a challenge to then fluidize these in your bed to actually do the coating?
Yeah. That's spot on. That's indeed problematic because on the one hand, often they are not inorganic but organic in nature, and those particles are already often a bit more cumbersome to fluidize and more sticky. And second, with this specific application, inhalation drugs, to get them at the right position in the lungs, you want to have particle size of 5 micron or so. And if people in industry design a good fluidized bed, then something like 50 or 80 micron is like the sweet spot, and 5 micron is a terrible particle size to work with if you like to get the best type of fluidization. So there we needed a lot of this fluidization assistant and twiggling around with vibration, for example, to get that well. Yeah, that's right.
Yeah, that's really interesting. So then, you mentioned these three applications. I'm definitely familiar with the controlled release, controlled release application, and so I presume that the coatings for each of these types of applications might be different. Do you use both ALD and MLD, or is it just one or the other?
Now we've been studying a little bit of MLD. One of the challenges is that for quite some pharmaceutical powders, you have to stay at rather low temperatures in order not to degenerate the pharmaceutical itself. I'm typically talking about 60 degrees C or something like that. So we've been using more ALD with pretty reactive reactants in order to get this well, and even the fundamentalists might say, well, then it's no longer ALD because you're outside the ALD window, which is in fact right. So you could, but with for example, trimethylamine, that works perfectly fine, and also with the chlorides to make silicon and silica layers and titania layers, silicon chloride and titanium chloride, that worked really quite well. And the good thing actually about particle ALD, since you have such a large surface area and you need a long time to cover everything, you can control the amount of precursor you feed quite well. I mean, if you have a wafer, you have to be very precise. If you wouldn't have self-saturation, because you're outside the ALD window, you quickly oversaturate. But for the particles, you need so many materials, so many reactants to get up to the point of saturation anyway. It's easier to prevent an overshoot over there. Right?
Did you then use some like kind of microdosing strategies then, almost kind of pulsing in precursor at a time, so that you never reach that point where you might go over? Or I suppose even if you're doing some type of MLD, you might not even have a precursor that has a good vapor pressure to reach that.
Yeah, that's a problem, especially with MLD. On the other hand, with the ALD, we also sometimes used a bit a very practical chemical engineer's approach. Well, if you overdose a little bit, maybe it's not pure ALD anymore, but we have a slight CVD component. Who cares? If you get the desired controlled release behavior in the end, it's fine, right? But still, we were typically in GPC growth per cycle ranges that normally you would also get with ALD. That's to be said that was especially for the titanium and silica. For the alumina, we saw that we got more kind of a vapor phase infilling type of behavior, because you're working with an organic, so you can apparently get some infiltration in there. And what was very interesting, that there's a distinct difference. You get really films on the outside with titanium and silica, and alumina, the trimethyl aluminium, is apparently so much more reactive that it goes into the pharmaceutical particles. A drug called budesonide in this case. It's really infiltrating, and you get more a zone of some tens of nanometers thick instead of a film of a couple of nanometers on the outside, titanium and silica.
Would this interface layer then affect how the controlled release happens? Which maybe is another question, what the mechanism.
No, but we checked that, and the very interesting thing was that roughly the thickness of the layer, so to say, and either being it a film on the outside or an infiltration zone on the inside, that the thickness of the layer was more or less determining how much it was slowed down. So there was not an enormous difference in being a film on the outside, infiltration on the inside. There was not much difference between titanium and silica and alumina. It was mostly the thickness of the film determined by the number of cycles. That was determining how much you're slowing down the solution.
That's really interesting. Does that then indicate that this proceeds by some kind of diffusion through the film? Is that how the drug is released from it? Is there dissolution of the film, or do we maybe not know exactly how it works?
No, that's a very good question. No, we still not 100% sure what is going on, and we making some diffusion models, see if that's part of the story, or that also over time you will damage some of the particles. We've been looking under single particles under a microscope what's happening. My best guess at the moment is that it's kind of a combination of phenomena playing a role over there. It's a bit a messy system, and that in the beginning you might have diffusion, you might have some pinholes through which material is being released. Yeah, and then at some point more and more particles might either break or bigger flakes of your coating might go off, and then the release goes faster.
It's such an interesting application for ALD. I don't think people might have ever thought about. I mean, particularly because maybe the materials are like, oh, can you even put that in your body? Is that?
That's a very interesting next one, because when the PhD student working on Damiano went around halfway to some presentations, some people in the audience responded, yeah, that's a crazy idea to put alumina on a drug that you're going to inhale, or to put this in your lungs. And we talked to our AstraZeneca collaborators about it, and they said, oh, maybe it's not that bad. It's small amounts, really small amounts you're bringing in, because you're not inhaling normally a lot of powder, and then on this small amount of powder there is some nanofilm of alumina, and basically the air that you breathe, and especially when you walk at the beach, and there is some silicon being facing attrition, you get this inorganic stuff in as well, and your lungs deal with it, and they get it out again via the mucus and so on. So there are mechanisms to clear that, and as long as this material doesn't have problematic shapes, and I think especially like needles and rods, those are notorious. We know needles from asbestos, and more recently carbon nanotubes are suspect to be dangerous, because apparently those get into your lungs and maybe might even puncture through the material inside your lungs. And that's the tissue that there was the word I was looking. So if they puncture tissue and so on and stay over there, then it gets problematic. But apparently, with these flakes, that's less of a problem. And well, we knew that when starting this project for duration for 4 or 5 years, we would never made it to testing it on patients. But what we've been doing is at least trying these drugs with some cell viability studies. So you have some in vitro cell viability studies. There was no harm shown whatsoever. And what was also tried to do, they have an AstraZeneca test where they take some lung tissue and bring it in contact with the material and see if it's harming. And also that was not a problem. So there are really good indications that it's not that problematic to have small amounts of, for example, alumina for this.
That's fantastic. I would have presumed that would be very interested in having more organic bioavailable coatings versus inorganics, but it's nice that they don't affect too much at all.
No, yeah, I agree with you. That would perhaps be optimum, but since MLD is already harder to achieve than an ALD, and if you then further limit your space in MLD by saying, but it must even be biocompatible organic coatings that I'm making, there are of course a number that's like PEG and so that they often use in pharmaceutics, which you can easily do in liquid phase. But yeah, there are not that many that would be straightforward to make with an ALD like system.
When I did my MLD on particles, I was doing nylon essentially, which was maybe not the most interesting for the pharmaceutical company to want in something like that. But I had looked at a lot of polymers that might be bioavailable or biocompatible, and they're just MLD's not there yet to.
No, that has somewhat longer to go still. Yeah.
Well, I do have a question that's maybe kind of an outlook, and it's not necessarily about ALD, but it's something I've thought about a little bit in the past. Is do you have any outlook or plans around particle etching?
That's a nice one, because you see, of course, new areas coming up in ALD related fields. And of course, going to the ALD conference, I see also that there are growing ALE community coming up. But so far, I really haven't seen it that much. Practically speaking, I didn't come across a very good application myself yet, where I thought, well, here we really should go for. And I think you can also say from maybe in a theoretical point of view, you could also argue whether it's really making sense. Because in ALD applied to particles, you need much more material that you deposit on the particles. So as long as you keep that material and it's in your end product, then it might be worth doing it. But as soon as you start in etching, so first you bring up material and then you start removing again some of the material, which is of course fine on a wafer when you want to make a high value microelectronic component at the end. It might easily pay off to do that. I doubt if on the scale of powders, where you really have to think well of the economics and talking about perhaps cents per kilogram that you can spend, whether it's making sense to first put on material and then remove it again. Maybe there are some very specialty applications, high value, where it could work. but not very generic, I would say.
Yeah, does it not appear that there is anybody really moving towards that type of research?
I don't remember whether I've seen anything like that. And yeah, of course, you could just do it out of scientific curiosity, but yeah, my research is typically quite application driven. Of course, we want to understand what's going on and we want to go into the fundamentals, but often with the final application in mind. This is why we want to understand the fundamentals to go there. Yeah, and I said for etching particles, I don't really see that at the moment.
Is there any kind of theoretical arguments for when you get down to small particle sizes to etch them, that like etching maybe won't even work that well? I know some kind of abstract concept for a lot of people is like the surface energy of a particle and kind of these agglomeration and aggregate formation. Would you see that being a barrier for ALE of particles at all?
Oh yeah, that could become interesting indeed. At those levels, and I think anyway there are a lot of things that are not very well explored yet. I mean, we didn't talk much yet about island growth on particles, but especially when you make catalysts. But that's interesting that you start with some inorganic carrier and you put islands of catalytic material on it. But also their surface energy might play an important role. First of all, you get the islands because of surface energy considerations. That apparently it's more favorable to form islands and nanoclusters instead of spreading out as a film. But when you go away from a well-defined wafer or well-defined surface to a particle, perhaps a nanoparticle with many facets, with different crystal planes and different energies, you might also imagine that the deposition on the one plane is different than on the other one. And I think that's an area where there's still a lot of room for research. That there's not much done on that one. But there already surface energy is playing a role. And if you would even bring in etching to that, you're completely opening a can of worms, I would say. So,
and maybe we'll keep Pandora's box shut for
yeah.
That is great. Because that I think is a nice way for us to bring it to the end here. Ruud, thank you again for joining me today. This has just been such a wonderful conversation, and I hope that everybody listening has had a great time and has learned a little bit about particle ALD. I hope you've had a nice time. It's been really great to really finally meet you and chat with you, and it's really been wonderful having you on, Ruud.
It was a pleasure being on the show, being on this podcast, Tyler. So thanks a lot for the invitation.
Yeah, absolutely. Okay. And to everybody listening, please check out Ruud's website, Twitter, and papers, and we will see you next time on the ALD Stories podcast.
You're listening to ALD Stories with Benek, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.